We conclude our introduction to problem-solving techniques for analyzing 1D constant acceleration motion with this third mini-lesson. We now know that there are essentially three types of 1D constant acceleration problems. The simplest, which I've labeled 0, involves a single object whose motion is in a single time interval, or segment. An example of this type of problem was worked in Part 1. There are two routes to making constant acceleration problems more complex. The first still considers only a single object, but whose motion is best divided into two segments, in which the final event of the first segment is the same as the initial event of the second. We worked through an example of this type of problem in Part 2. The other type deals with two objects undergoing constant acceleration, whose motions are somehow related to each other by conditions prescribed in the problem. Let's do an example of this type of problem. A Ford Leviathan SUV zooms past a parked police patrol car at a constant speed of 36 meters per second. The patrol car begins pursuing the speeder 2.0 seconds later, accelerating at a constant 1.0 meters per second squared. Part A asks, when does the patrol car catch up with the SUV? And Part B, how far have they traveled when this happens? As usual, our first job is to parse the problem into events. From the information provided in the problem, and from the quantities we are asked to calculate, it's clear that there are three events. 1. The speeding SUV passes the parked patrol car. 2. The patrol car starts accelerating toward the SUV. And 3. The patrol car catches up to the SUV. The SUV, we're told, travels at constant velocity throughout. That means its acceleration is the same constant value, 0, for the entire time. So the initial and final events of its motion are events 1 and 3, respectively. The patrol car, however, stays put between events 1 and 2, at which point it begins accelerating at a constant 1.0 meters per second squared. So the initial and final events of its motion are events 2 and 3, respectively. Our next job, as always, is to sketch the problem. Here I show three snapshots of the motion arranged in parallel, each one depicting one of the three events. Let me emphasize that the sketches are not meant to be to scale, they're just schematic. In particular, I have a feeling that the spacing between events 1 and 2 is a lot smaller than that between events 2 and 3, and we'll see later if I'm right. By now you know what comes next. We construct a model that eliminates extraneous details so that we can focus on the essential details. We'll still use a particle model, but since we have two objects, we'll need two particles. To keep the two particles straight, I've color-coded them. The SUV is modeled by a red particle, and the patrol car by a blue particle. We start with the red. Each dot represents the SUV at each of the three events. I've used a subscript S to denote quantities associated with the SUV, and I've also color-coded the text to match the dots. Since an event corresponds to a specific snapshot in time, the time for a given event is the same for both the SUV and the patrol car. So there is no letter in the subscript, and the color of the text remains black. Since the SUV moves at constant velocity, its velocity variable has the same value at each event, 36 meters per second, and the arrow is the same length at each event. Furthermore, the acceleration is 0 the entire time, so I haven't bothered with a numbered subscript. Now on to the blue dot, which is the patrol car. Here I've used a subscript P on its variables, and I've color-coded them blue to match the dots. Since the patrol car doesn't move between events 1 and 2, its blue dot stays in the same location, and its position and velocity variables are both 0 for both events. At the third event, it is moving, and its velocity has to be greater than the SUV's in order for it to have caught up. This is indicated by a longer arrow. Furthermore, the position of the third event is the same for the SUV and the patrol car, as implied by the phrase, catch up. Therefore, I've used a single variable, x sub 3, to represent this position, and I've left its color black. As always, unknowns are indicated by question marks. And this problem has three unknowns: the time of event 3, the position of event 3, and the velocity of the patrol car at event 3. We are now ready to set up equations and solve for the unknowns. Since the motion of the SUV is simpler, we'll start by writing an equation for its motion. In particular, here is the first constant acceleration equation for the case of the SUV. Remember, its initial event is event 1, and its final event is event 3. Since its initial position and time and its acceleration are all 0, this equation simplifies considerably to x sub 3 equals v sub s times t sub 3. Substituting in for v sub s yields x sub 3 equals 36 times t sub 3. But since x sub 3 and t sub 3 are both unknowns, we can't go any further with this equation. One thing to point out, I've left off units on the coefficient 36 just for convenience. We'll put back in the units later. So let's move on to the patrol car. Here again I'm using the first constant acceleration equation. But notice that since the initial and final events for the patrol car are events 2 and 3, respectively, the subscripts are 2 and 3 rather than 1 and 3 as they were for the SUV. The initial position and velocity of the patrol car are both 0, so this equation also simplifies considerably. Notice, however, that the initial time for the patrol car, t sub 2, is not 0. We have to keep it around. Now we substitute in the given values for the acceleration and the initial time of the patrol car's motion. When we multiply out the square and drop the units, again for convenience, we're left with x sub 3 equals 1/2 times the quantity t sub 3 squared minus 4t sub 3 plus 4. We now have two equations for x sub 3 in terms of t sub 3. Therefore, we can set the two right-hand sides equal to each other. Moving the left-hand side over to the right-hand side and combining like terms gives the equation 0 equals 1/2 t sub 3 squared minus 38 t sub 3 plus 2. This is a quadratic equation, so we expect there to be two solutions, which are found using the quadratic formula. Evaluating and putting the units back in give t sub 3 equals negative 0.05267 seconds for one solution, and t sub 3 equals 75.947 seconds for the other. But which one is the answer we're looking for? Well, we know that the patrol car doesn't even start accelerating until time t sub 2 equals 2.0 seconds. So it doesn't make sense that it would catch up to the SUV at a negative time. The physically sensible solution for this problem is t sub 3 equals 75.947 seconds. Now that we know t sub 3, we can plug it back into one of the original equations to find x sub 3, and that gives x sub 3 equals 2,734 meters. Now we're ready to answer the questions in the problem. The patrol car catches up to the SUV 76 seconds after the SUV first sped past the parked patrol car, or 74 seconds after the patrol car started to accelerate. This happens after they've traveled 2.7 kilometers. Notice how I've kept only two significant digits in these answers, because two significant digits are all we're provided in the write-up of the problem. It's always a good idea to assess the reasonableness of the answers we get. Do these numbers make sense? Well, the time certainly seems reasonable. It shouldn't take the patrol car just a few seconds or tens of minutes to catch the speeder, especially if the cop keeps accelerating. The distance is also a reasonable amount, smaller than, say, a country, but larger than just a couple of meters. Okay, a final question for you to consider. What about the third unknown, the final velocity of the patrol car, v sub p3? Well, the problem doesn't ask you for it, but that doesn't mean you can't calculate it if you want to. Just for fun. All right, go ahead and give it a try.